So we'll go over this kind of freezing point problem. It's similar to one that you guys had on an exam. I think it was exam number 4 or number 3. So I like this because it kind of puts together a couple of different things for us. It has a little bit of empirical formula in there to begin with, and then we build from that into kind of identifying it. So we'll start with this first part. And we want to calculate the empirical formula of this hydrocarbon that's 93% carbon and 6.54% hydrogen. So that's 93.46 grams of carbon to 6.54 grams of hydrogen. I'm going to turn that over into my moles. So 93 divided by 12 becomes 7.788 moles. 6.54 divided by 1.00794 becomes 6.488 moles. And so I'm going to divide each one of these by the smallest value there. So this becomes 1.20. This one becomes 1. And so what do I need to multiply them by to get rid of that 0.2? What number should I multiply that by? You guys have any thoughts? If we wanted to get rid of that 1.2 and turn it into a whole number, what should we multiply it by?
10.
So if we multiply it by 10, we're going to get 12 and 10. So carbon 12, hydrogen 10. Is that the lowest ratio that we could do?
No.
No. All right. So then we can bring that down and we can make that C6H5. So we could have multiplied it by 10. You just have to reduce it, or you could just multiply it by 5. Both of those will work. And so that's how we got our empirical formula. Now, empirical formula is useful because it's the ratio of our carbons to our hydrogens, but it doesn't tell us about our moles. And so this second part with our solution data, we're going to calculate the molality so that way at the very end, we can use it to find this molecular formula. So we're going to run this next part here. All right. Now I'm going to erase this bottom part to make some space for it. And so you can kind of treat this like it's a new problem for now, and then we can pull that data together later on. And so it's saying that a solution is prepared by dissolving 2.53 grams of dichlorobenzene, and it's got a molecular weight of 147 grams per mole, in 25.86 grams of naphthalene, which has a molecular weight of 128.2. And it wants us to calculate the molality of that dichlorobenzene. So it wants us to think about the moles of the dichlorobenzene divided by kilograms of what? Is it going to be the kilograms of the solution, or is it going to be the kilograms of just the solvent? So for molality, it's not kilograms of the solution, it's just the kilograms of the solvent. So that means that we can take these moles of the dichlorobenzene. I'm just going to shorten it as TDCB. And then I need to take the kilograms of that naphthalene. Right? So my moles is 2.53 grams. 1 mole is 147.0 grams. And then my kilograms is 25.86 grams. 1,000 grams is 1 kilogram. So I get something that looks like this. 0.0172 moles divided by 0.02586 kilograms. And so our molality is 0.6655. Do you guys have any questions about that molality part so far? So sometimes for your note card, I do recommend putting your units for your concentration on there because it's a very common mistake to think it should be kilograms of solution, right? It's because molarity is solution, molality is only the solvent, mass percent is solution, mole percent is solution, ppm is solution, right? So many other things are all in solution, but molality is in solvent. And so now that we have the molality, it's saying that, well, the freezing point of pure naphthalene is 80.2 degrees Celsius. And we're saying that the solution B is found to have an initial freezing point of 75.7 degrees Celsius. And so it wants us to calculate the depression constant. Now, the units for depression constant is delta C per molality. So what we want to do is we want to calculate how far have we depressed our freezing point for this solution. And then we want to calculate how much molality do we use to get there. So if we want to figure out how far down it's gone, we take the 80.2 degrees Celsius, we subtract the 75.7 degrees Celsius, and this tells us how much we've depressed our freezing point. Right? We've lowered it 4.5 degrees. That means that for an additional 4.5 degrees, it's in the liquid state instead of becoming a solid. And we know that happened because of the 0.6655 molality of our solution. So if we want to find the constant, we divide 4.5 by that 0.6655, and we get 6.76 degrees Celsius per molality. So if we had increased the concentration of the dichlorobenzene inside that solution, if we brought it up to 1 molality, we would have brought down our freezing point by 6.76 degrees Celsius. Do you guys have any questions on that part? Okay. So our next version of, or the next part of this question is saying, well, let's take that hydrocarbon that we had from part A and let's dissolve it in 26.7 grams of naphthalene. And we're going to use 2.42 grams of it. So we find this freezing point to be 76.2. What it wants us to do now is it wants us to calculate the molecular weight. Oh, dang it. Let me see. All right. Sorry, I hit the wrong erase button and now I cannot bring that back. No, all right. So we knew that this was C6H5 We know that this one is 6.76 degrees Celsius per M. We don't actually need to know this part, so that part's fine. And so it wants us to go back and we want to try to find this molecular weight. So the first step is I want to figure out how far I've depressed my freezing point. So I've depressed it 4 degrees Celsius. And so what I'm going to do is I'm going to look for my molality. So if I take this and I divide it by my 6.76 degrees Celsius per molality, you can kind of imagine it's almost like doing it like this. It's going to tell me the concentration of my solution in molality. So that tells me that I have 0.5917 moles of my naphthalene in 1 kilogram of my solvent. Now, I don't have 1 kilogram of it. I only have 26.7 grams, so 0.0267 kilograms. And so it tells me that I have 0.0158 moles of my naphthalene. Now, did it ask us only to find our moles, or do we want to find a molar mass? So for part D, is it asking us to find the molar mass, or is it just asking us to find the number of moles? It should be asking us for a molar mass. So if we take the 2.42 grams and we divide it by our number of moles, we can get our molar mass as 153 grams per mole. Do you guys have any questions on that part? Yeah. So now if I go ahead and erase this part, I'm going to ask you, what is the molecular formula of our compound? So remember to go from your empirical formula to your molecular formula. We know that there's 153 grams per mole, and that's going to be equal to n number of sets of C6H5. So that 153 grams per mole is equal to some number n times, and the molecular weight of C6H5 is 77.06 grams per mole. So if we take that 153 and we divide it by 77, we find out that n should be 1.985, so just about 2. And so our molecular formula should be 2 times C6H5, which is really C12H10, right there. And so that's one way that you can use your colligative properties. If you know that they're non-electrolytes, you can use it to figure out your number of moles, because then you can tie that in with your freezing point depression in your colligative properties. Any questions on that part? Are you guys still there? So this is all one problem. This would be not one problem on your final exam. Right? On your final exam, we would break this up into more pieces. In person, I generally like these style of questions, but because of the way that the online format is, I can't get them to work in the online one. So we would have broken this up. We probably would have had the empirical formula going into your molecular formula as one. And then we would have just found either part C or part D as separate ones. So for your final, we'll have these broken up into more pieces. But yes, this is all one style of problem. What I encourage you to do is when you study is I would work through problems like this because it helps you identify better where your weaknesses are. So you'll be able to see where things kind of fall apart for you. If they always fall apart in the same place, then you know what you need to kind of study. So the other part that we wanted to look at was we wanted to look a little bit into our yields. And so we're going to jump over to slide number 18. I'm going to look at this problem here. Now, this is a hard problem. It's got a lot of things going on in it. So we're going to take our time. We'll break it down. And so we'll kind of work our way through this one. So I'm going to go through, I'm going to read through and highlight some stuff. So we have a mineral and it only contains hydrogen, oxygen, and then some unknown metal M. And so it's giving us this ratio here for our empirical formula. So we know that 1 gram of this, when it's heated, decomposes into oxygen and water vapor, and then MO3. Now it tells us that we're going to get a 1 liter container of it. It's going to be at a specific temperature and a specific pressure. So 1 liter, 200 and 200. And then they're going to talk about that we are going to cool the container. And then it gives us that vapor pressure of our water. Okay. So there's kind of a lot going on. So we're going to take the first part. We're just going to break down our formula so that way we can have kind of like our chemical reaction there. I always find it easier for me to imagine what's going on when I have my chemical reaction right now. So I'm going to take MOX, H2OY. I'm going to turn that into O2 gas plus H2O gas and MO3 as a solid. So I collect it inside of a container here, which has a volume of 1 liter. And I collect it at a temperature of 200 degrees Celsius and a pressure of 355.0. Now, once we move down, our pressure falls. So we go to a volume of 1 liter still. Our temperature now is only 25 degrees Celsius. And our pressure is 48.65 millimeters of mercury. So inside this container at my low temperature, what gases do we have present? What gases do we have present? We have water and O2. Very good. So we got H2O and O2. Now we know how much water we have because they give it to us in this foam or vapor pressure. So out of that 48.65 millimeters of mercury, 23.80 of that is water. So if we want to find the moles of our O2, we know that that should be PV over RT. And we know that the pressure should be 48.65 minus 23.8. So 24.85 millimeters of mercury, 1 liter, 0.08206 liters atmosphere, K mole. And my temperature, 298 Kelvin. So I'm going to take that, I'm going to divide by 760 to turn that into my atmospheres. And so this becomes 0.0326. 270 atmospheres. So I'm going to multiply that by 1 liter. I'm going to divide that by 298, divide by 0.08206. And so my moles of my O2 is 0.001337. You guys have any questions on that part so far? So after that, they want us to calculate the moles of our water. Now to do that, we can't do it at a low temperature anymore. Because at a low temperature, some of the water is turned into a liquid and we don't know how much. So instead, what we're going to do is we're going to go back up to the high temperature when all of that water was a gas. And so we're still looking at the same thing. We're looking at our pressure of our oxygen plus the pressure of the water. And now instead of being 48.65, it's going to add up to 355. Now I want to subtract the pressure of my oxygen, so then I can find the pressure of my water, and then I can plug that in for water. Into that same expression. Now we know the moles of our oxygen, so we just need to convert that over to what its new pressure would be. We can't just use that 24 because it's at a different temperature. So we can take 0.001337 times our R, and then our new temperature, which is 473 Kelvin, divided by our volume, 1 liter, and this will give me my pressure of my oxygen. I'm going to change my 355 to atmospheres. So my pressure on my water becomes 0.415. My volume is still 1 liter. My R is 0.08206. And my T is 473 Kelvin. So the moles of my water is 0.010697. All right. So that's how we can solve that part of it. Do you guys have any questions on that? So this next part is it wants us to know how much MO3 we have. And so our MO3 doesn't show up in any of this stuff with our ideal gas law, so we can get rid of all of it. How can we figure out how much MO3 there should be? What do you guys think? Any thoughts about where we should start with this kind of a problem? So when you're saying it's confusing, which part is confusing? So to convert to atmospheres, 1 atmosphere is 760 millimeters of mercury. And so that's what I've been using for that conversion. So that's on your equation sheet. You can see it. It's up there with the ideal gas. Same thing for the conversion into Kelvin. So we knew that all of this material starts off as 1 gram. So it all started off at 1 gram. And then the other part is that the material goes into oxygen, water. So I'm looking at this section over here, right? It goes into oxygen, water, and then this MO3. Now we know how many moles of oxygen we got and how many moles of water. So if we know the moles of them, can we figure out how much those weigh? If we know their moles, can we figure out how much they weigh in terms of grams? We should be able to. What we want to do is we want to turn them back into grams. So that's going to be their molar mass. So O2 is 32 grams per mole. Our water is 18. Now, when we add those two together, we get a total of 0.2345 grams. Now, yes, we've been finding moles for our PV equals nRT, right? So we haven't been finding grams, we've been finding moles. So now that we have them inside of their mass, right, is that 1 gram sample all accounted for in this one? So if we've turned both of these into their mass, so we have our grams of our O2 and we have the grams of our water, their total is this 0.2345 grams. Is that accounting for all of the mass of the sample? So it's not. And so that extra mass is going to be our MO3. So we start off with 1 gram. We have 0.2345 grams left now. And so our mass of our MO3 is 0.7655 grams of our MO3. And so that's how we can figure out this part down here. Does anyone have any questions on that? Okay. So the last part is a little bit difficult, but actually I think that they explain it out really well down here. I would say that I wouldn't worry too much about trying to identify your unknown. This one's a little bit more involved than something I would give you for your final exam. And so I don't want to spend too much time on it, right? I'd rather hit on your other questions, but they have a good explanation that comes in afterwards where they kind of walk you through it. And so if you're feeling confident with everything else, then I would worry about this. If you're not feeling confident with it, then I wouldn't worry about it as much. But it's this concept of you can find the ratios between them, between what your oxygen should be produced, and then we can actually backtrack out what the molar mass of our M needs to be based on how many moles of oxygen compared to the moles of water you made. But either way, I don't think that's something that's really worth spending too much time to figure out. So I think that's okay. Is there something else that you guys would like to see? Because there's a lot of different kinds of material that we can go over. So I think I'm just looking for some feedback from you guys about what you think is a worthwhile part, what you kind of want to would like to work through. Okay. So when you say heat enthalpy, do you want something like this where you're finding the delta H of something, or are you talking about like a calorimetry problem where you're looking for the heat that a sample gains? Okay. So we did do one, something similar to it at the very beginning, right? We worked through one that looks like this with a phase diagram. But we can do another one where we have a container and we're going to put some water inside. So the mass of that water is going to be 100.0 grams. And we know the specific heat of that water is 4.184 joules per grams degrees Celsius. So that's our CS. Now, to that sample, we're going to add something. We're going to add in a piece of metal. Now that metal has a mass of 60, or that's a 4. .65 grams. And it started out at a final temp, or at an initial temperature of 85.0 degrees Celsius. Now our water started off at room temperature. So it started off at 25 degrees Celsius. And both of them end up at the final temperature of 22.1 degrees Celsius. What we would like to do is find out the specific heat capacity of that metal from that information. So in this scenario, what do we know about the heat of the water and the heat of the metal? Is there a relationship between them, or do we not know anything about them? How is the heat that the waters gain related to the heat that's lost by the metal, right? And you're right, the heat of the water is going to be the negative value of the heat that's lost by the metal. One's going to be positive, one's going to be negative, but they'll be the same magnitude, the same size. So if we want to find the water becomes Q equals MC delta T. So we have our mass, 100.0 grams. We have our C, 4.184 joules, grams degrees Celsius. And what should the delta T be for the water? Oh, sorry. I gave you the, instead of 22.1, let's make this 27.1. That'll make more sense. So the delta T isn't just its initial. Its delta T is its change, right? That's why it's the delta sign. So what's the change in temperature? TF minus TI. And so what value should that be for our water? (2.1), very good. Sorry about that. I gave you a problem that wouldn't have worked before. Right? So this is our 2.1 degrees Celsius for our delta T. And on the other side, for our metal, we know the mass of it, 65.0 grams. We don't know its C, but do we know its delta T? What should the delta T be for our metal? I'm going to put a negative sign in front of here, since we should have the negative of that Q. So 27.1 minus 85 becomes negative 57.9. Very good. That being degrees Celsius. So I'm going to go ahead and erase this so we have a little bit more space. I'll put that over here. So we can consolidate the whole left-hand side. So 100 times 4.184 times 2.1. All of this becomes 878.64 joules is equal to, and then we can consolidate a lot of this part. So 65 times 57.9. And both of those are negative, so we should have a positive value now, 3,763.5. And that's going to be our grams times degrees Celsius. So if we want to find our CM, we just need to take 878.64 divided by 3,763. And we get 0.2335 joules per gram degrees Celsius. And so that's how we found our specific heat capacity. So you want to practice, you can use this to find a lot of different things. Sometimes you could find the mass of a sample. You can also find what final temperature they should come down to. So it all kind of depends on what you're doing with your problem. Is there another topic that you guys would like to see? Do you want to see more theoretical yield ones, Armand, or do you feel more comfortable with that now? Okay, so one thing that I would recommend is don't forget that you should also have your trends, right? So you should know your trends, but you should also be able to explain them. And so we do have cases where you have like jumps in your trends, or you might have your different impacts of your ions. And so you do want to make sure that you practice explaining some of those. We also have something that looks like this for our atomic emissions, right? So we should be able to predict whether we're absorbing energy or losing energy or emitting energy when we're transitioning an electron. But we should also be able to tie in our wavelength with those energy values. And so this is that energy is hc over lambda, or cv equals lambda, and energy is hv, right? So making sure that you understand how those fit together. This one here, this is for the hydrogen atom, but I could give you any different value of that RH, right? The reason why they give you that H is to say it's for hydrogen, but we could also do like for a lithium atom, you could get an RLI, and you could look at those energies. It would just be a different constant that you're putting in that same equation. And just remember that the reason why you get negative values for those delta E's is a negative value means that you're emitting that photon because you're losing that energy. It doesn't mean that your wavelength is going to be negative. It just means that that electron is being released away from the atom. If you get a positive value, it means you're absorbing that photon. So that's why it's your initial minus your final. Is when your initial is higher than your final, then we should get a negative value because we should be emitting it. When your final is higher than your initial, then you should get a positive value because you should be absorbing it. And so that's how that's set up for your equation sheet. You'll see them written in different ways, and it all depends on your book, because sometimes they've already adjusted the negative sign away because they're saying this is the energy that's emitted. And so they don't want you to have a negative of an emitted energy. All right. Any other questions of things that you guys want to go through? That's a good question. So let's see if we have a periodic table on this slide. I'm sure I have one in here somewhere. I just need to find one. All right. So we'll make this work for now for our periodic table. let's say that we're looking at sulfur. So sulfur is, well, not sulfur. Let's look at carbon. So carbon is this element here. Right? When we take away one electron, right? So we do one ionization energy, it's going to travel and it's going to move one spot over and it's going to look like that element there. When we remove a second one, so this is ionization energy 2, we start to look like this one. Number 3 moves us over to this box right here. Number 4 finally transitions us all the way over to that box. And then number 5 is when we move from our helium to our hydrogen box. So when we're looking for the big jump happens because we're removing a core electron. So when we think about it, how many valence electrons does carbon have? 4. So we can remove 4 electrons away and we wouldn't have removed any core electrons. So that's this first transition, 1. The second transition, 2. The third transition, 3. And we can even do this big transition, number 4. And all of those will be smaller jumps compared to when we finally do this last transition here, this one here. All right? And the reason for that is that on that 5th transition, so that 5th ionization, I guess it would be the right term for it. We finally remove a core electron. So when you're looking for the element based off of where the jump is going to be, you want to look at where the jump occurs. So this one would occur between ionization 5 to ionization 6. Or, sorry. So 1, 2, 3, 4. Sorry, between ionization 4 and ionization 5 is where our jump occurs. And so 4 is your maximum valence electrons. 5 is your core. So if we wanted to think about that, if we get that jump between 4 and 5, then our element should be X 4 plus. So we know what period we're looking for. And so now we're looking for some element in this column here because it's got 4 valence electrons. And that's kind of how you tell that difference. So if you have a jump and that jump is going to occur between IE2 and IE3, how many valence electrons do we have? So if the jump is between the ionization energy of number 2 and the ionization energy of number 3, how many valence electrons can we have? What do you guys think? So I'm going to give you some numbers and we can kind of see, right? Let's say that this ionization energy was 100, 250, 7,000, 8,000. Right? We can see that that jump happened between 2 and 3. This is where it really increased. So that meant that we could remove 1 electron. No problem. We could remove 2 electrons. Not a problem. But when we remove 3 electrons, then we have a problem. So our number of valence electrons, not 3, you're right, it is 2. It meant that we could remove 2 of them. So we could become X2 plus, no problem. But we can't become X3 plus without a lot of energy. So our valence electrons is 2 of them. So when you look for the jump, what you want to do is you want to go to the one right before the jump, and that tells you how many valence electrons you have. So in this case here, if I told you that this was in the 3rd period, what element would it be? So we're in the 3rd period, and we have 2 valence electrons. What element are we? Magnesium, very good, right? And that's kind of how you put that together with your ionization energies. Not a problem. Any other questions that you guys would like to go through?